Questions about anything? Today I want to show you a great thing. It's the complex version of Fourier series. And by complex, I don't mean complicated. It turns out that when we use complex notation for the trigonometric functions, the formulas become significantly shorter and easier. And it's going to be useful enough that that's the way we're going to do it in the future. So last time I determined that if a function could be expanded in this series, then by virtue of orthogonality, all those functions, cosine nx, sine nx, and the constant function 1 are orthogonal on the interval from minus pi to pi. And when you take that into consideration and multiply that thing by one of them and integrate, you come up with these formulas that the coefficients absolutely have to be those things there. And those are kind of it's annoying that there's different formulas for the cosine terms than the sine terms, etc. And it's a mess to write it all out. I should point out that in some books, I'll erase this in a second, they put a 1/2 in front of this term and then remove that 2 there. That makes at least that makes all the formulas start with 1/pi. So that's kind of a tradition in some books, but not all books. And I don't like that tradition, so I'm not going to do it. Because I like the fact that A0, the way I do it here, is the average of the function on that interval. And that makes sense. That makes sense if I were going to average that function. The averages of all the cosine terms and sine terms are 0. Because when they wiggle, they spend as much time above the axis as below. So the humps cancel, and those integrals are all 0. So it's very clear that A0 has to be the average of the function. Questions about that? Well, here's the complex version involving complex functions. So the key goes back to Euler when he started writing down the complex version of the exponential function. So if I write z equals x plus iy, complex number, then e to the z is equal to e to the x plus iy. And everybody knows the Taylor formula for e to the t. And Euler put x plus iy where the t is there, and realized that he could make sense of that as a limit, involving a limit of complex things. And he also realized that the same algebra used to show that e to the a plus b is e to the a times e to the b, exactly that same algebra shows that this e to the x plus y is equal to x plus iy is equal to e to the x times e to the iy. And if you put iy in the Taylor series, you probably did this someplace. This is 1 plus iy over 1 factorial plus iy squared over 2 factorial plus etc., etc. And you can split that into, let's see, I might also write a couple more here. Iy cubed over 3 factorial, or one more, plus iy to the 4th over 4 factorial, plus, and Euler pulled that apart and realized, okay, this thing has a real part. Let's see, the real part, there'd be a 1 there. I squared is minus 1, so it'd be a minus y squared over 2 factorial. And the next one would be plus y to the fourth over 4 factorial, because I to the fourth is back to being plus 1, and it alternates, etc. And then the rest, there's an I times y, that's the first complex imaginary part. The next one would be I cubed is minus I. So that would be minus y cubed over 3 factorial. The next one would be plus a y to the fifth over 5 factorial, etc. And you look at those and realize those are the famous power series for cosine and sine. And so, Euler, he made sense of all these things, and he made this sort of the definition of it. He did it. Yeah, I'm going to do it here, make this the definition, just to avoid proving a lot of things about complex analysis. We'll take these things as sort of given. Anyway, the real part of the exponential function in the complex realm is e to the x cosine y is the real part. And I times e to the x sine y. Math 425, the other class I'm teaching, is we spend a lot of time making sense of this thing that goes way back to Euler. And we get comfortable with it. You'll get comfortable with it here, but I'm not going to do it from sort of a foundational, motivating point of view. We'll take this as the definition of the complex exponential. Well, when you get used to writing this out, you'll notice that if I just take e to the I theta, that's taking x equal to 0. And so the e to the x's would be 1s. And there I would get cosine theta plus I sine theta. And e to the minus I theta is cosine theta. Cosine of minus theta is cosine theta. And sine of minus theta is minus sine of theta. It's an easy thing to check. E to the minus I theta is 1 over e to the I theta as a complex number. Because sine squared plus cosine squared is 1. That's why that is an easy calculation. Anyway, that's a remark. And so let's see, what am I going to do here? I want to show you the famous formulas that Euler came up with. If I add these two things together, then I get cosine 2 theta on the right, and over on this side I would get e to the I theta plus e to the minus I theta is 2 cosine theta. The sine thetas cancel out. And so, interesting formula, cosine of theta can be expressed in terms of the complex exponential as e to the I theta plus e to the minus I theta over 2. And if I do the minus above in that thing instead of a plus, well, then the cosines cancel, and I get an I sine theta plus I sine theta when I do that. That's 2I sine theta. And when you solve that one for sine theta, you would get sine theta is e to the I theta minus e to the minus I theta. This time we have to divide by 2I. Okay, those famous formulas. And Euler also realized if I'm going to define cosine and sine for complex numbers, that's how I would do it. I'd replace the theta with a z. And that's exactly how the trigonometric functions are extended to the complex plane. Okay, so let's see. I've got, let me, instead of rewriting this thing, let me copy it. Oops. I'll go back to the top. Oops. What happened? There it is. I'm going to copy this thing. No, I'm just going to... There it is. Okay. So, we're going to hope that our f of x is equal to this thing. Okay, and I'm going to use the fact that cosine here is going to be an e to the I nx plus e to the minus I nx over 2. And I'm going to use the fact here that sine nx is e to the I nx minus e to the minus I nx over 2I. And then when I combine them, I get that this Fourier series could be a naught plus the sum as n goes from 1 to infinity. Let's see, when I pull them all together, I'll get some e to the I nx terms. And let's see, those e to the I nx terms would be a n over 2 from the first one there, and b n over 2I. Bn over, let's see, bn over 2, now I in the bottom can always be brought to the top because 1 over I is minus I. So this is actually minus I times bn over 2. Okay. And now I also get stuff times e to the minus I nx. And let's see, when I get this, I would get an a n over 2 again for that from the first term. But this time, I'd get a minus 1 over I, which is a plus I in the top. So that would be plus I times bn over 2. I'm going to call this thing here a complex number, Cn. And I'm going to call this one a C minus n. Okay. I claim this is going to be a beautiful, clean way. I'm going to show you something in a second. Let's see. Let me first start messing around with C sub positive n. C sub positive n is 1/2 an minus ibn. And that's, let's see, 1/2, put a 1/2 here. And then remember the an's and bn's are 1 over pi integral from minus pi to pi. The an is, I'll put a square bracket here, integral cosine nx. And a minus I times bn, that's a minus I sine nx dx. That's interesting. This is e to the minus I nx. And so I get a very simple, nice formula for the C sub n. C sub n is equal to 1 over 2 pi, which is the length of the interval, nicely, f of x times e to the minus I n x dx. That's a nice formula. And if I put n equals 0 in there, well, I would also get a C naught. Let's let my C naught be A naught. That's equal to 1 over 2 pi integral from minus pi to pi f of x times 1. And that 1 is e to the 0. It's, well, actually, it's e to the minus I times 0 times x. So that formula would also spit out my constant term. And amazingly enough, exactly the same. So here's a great thing. The Cn formula holds for the negative terms. By replacing the n by minus n in both spots. So C sub minus n, I'm going to get minus minus n when I do that there. So I get one formula fits all the coefficients. And that's nice. That's so nice that that's what Euler was famous for, is finding simpler ways to write everything. That's easy to check. I won't write it out. You just write it out and see that that's true. Check it. It's just a write out. As I did above. Okay, so there's one formula, and I'll put it in a box. Well, let's see. Let me summarize what I've got here. Summary. The complex version of the Fourier series is f of x, hopefully equals summation Cn e to the I n x, as n goes from minus infinity to plus infinity, of where Cn is 1 over 2 pi, one formula for all the coefficients. Let's see, so the C plus n would have an e to the minus I n x in the complex integral. Okay, so we got to get comfortable with complex functions and integrals, and thinking of that as a inner product. Okay, so I'll spend some time doing that today. So if we had a real inner product, I've been using the real inner product when I was doing Johann's solution. And then I would write FG inner product. In the case of the interval from minus pi to pi, it's a real integral of f of x times g of x dx. Okay. We're going to do the same thing with complex functions, but then you might remember when you did inner products for complex vectors, it was critical that there be a conjugate in the second variable when you dot product. Okay. Did everybody have a linear algebra where you did that kind of stuff? And there's things like Hermitian structures to think about. Well, I'm going to do something similar here. Let's talk first about integrals of complex valued functions. Complex valued functions of a real variable. That's kind of as far as we're going to go in this course. In Math 425, we studied complex valued functions of a complex variable. We'll come close to that in here, but not as far as we go in 525. So complex valued functions of a real variable. So example, let's write how about capital F of t is a real function, u of t plus I times v of t. That's how you would express such a thing. The real variable's t, and it's going to map to a complex number, which is u plus iv. And so those u's plus iv's would depend on t. Then I could make a Riemann sum if I wanted to, and say the integral of f of t dt from minus pi to pi is a limit of a Riemann sum. So it's a limit of summation f of ti delta ti. I would go from 1 to n as the delta t's go to 0. And I could play games and say I got to make sense of that and realize, oh, when I do this, it would split into a sum. And the sum would, let's see, the real part would be the sum of uti delta ti the Riemann sum. And then I'd have I times the imaginary part. So it's a very natural thing to say, gee, if I'm going to do this in a traditional way that anybody would think of, I'm stuck with the definition of the integral of a complex function being just the sum of the integral of the real part plus I times the integral of the imaginary part. Okay, so that's sort of that's going to be, we can motivate that and do all kinds of estimates and show, yeah, that's what it's got to be. But I'm going to take that to be the definition of the integral from minus pi to pi of a complex function like this. That was the convention I was using above when I was messing around with the formulas in Fourier series. Anyway, it makes perfect sense. And it kind of has to be that way. So an example, integral from minus pi to pi of e to the I n x dx. That would be the integral from minus pi to pi of, remember the complex exponential is cosine nx plus I sine nx. And that's equal to the integral of cosine nx. And it happens again here that cosine and sine wiggle exactly n times in that thing, and they have a hump. There's as many humps above the axis as below, and so without even calculating, I know this is going to be 0. equals 0 plus 0I. Of course, that's big fat 0. Okay. So now that I've played around with some integrals like this, the complex inner product, by convention, is, I'll take capital F's here to capital F and capital G. Those are complex valued functions of a real variable. They would be the integral from minus pi to pi. And you might be tempted to write f of t times g of t, but write, as you did in linear algebra, it's essential that the second variable here be a conjugate, so that the axioms of a complex inner product hold. Okay. And using this convention, a big fact is that those functions are orthogonal. E to the I n x, as then goes from 1 to infinity, are orthogonal in this sense on the interval from minus pi to pi. Yeah. Thank you. Why don't I do the calculation, because there's nothing to it. Let's see. Let's check it. Okay, so I would have here integral from minus pi to pi e to the I n x times e to the I m x dx. I got to put a conjugate over that second one. And now I use the fact that, let's see, e to the I m x conjugate is the conjugate of cosine mx plus I sine mx, and that's cosine mx minus I sine mx, and cosine mx is the same as cosine minus mx, and minus sine mx is I times sine of minus mx. So that integral is equal to the integral from minus pi to pi of e to the I n x times e to the minus I m x dx. And that fact, Euler determined the facts about complex multiplication of the complex exponential. It satisfies the same rule you learned for the real exponential. That multiplication is e to the I n x minus I m x. And if you were to write that out, you'd realize that was just a trig identity. If you write out in terms of real and imaginary parts, you'd say, sure enough, that's just a trig identity. In fact, that's how Euler proved it. Okay. Let's think about what this integral is now. This would be the integral from minus pi to pi of, let's see, this thing is e to the I n minus m times x. So that'd be cosine n minus pi n minus m times x dx plus integral from minus pi to pi. And this is the same thing I just looked at. Those integrals are 0. I have got two cases to consider. That's 0 if n minus m is an integer and not 0. So when n is unequal to m. Because the cosine and sine wiggle. Same number of times above as below. Or you can calculate the integral from using freshman calculus. But when n is equal to m, sine would be 0, sine of 0. That's always 0. So that, oops, I got, my eye goes here, sorry. I times 0 in that case. And the cosine 0 would be 1, so I'd get 2 pi when n equals m. Okay, so in fact I could do that same thing. Now that I've done this calculation, I could do the same integral let's see how much time. So if I think about how easy it would be if I were to write f of x is a summation of Cn e to the I n x as n goes from minus infinity to infinity. We want that. Let's see, I got to give myself some more room here. We want this. So what do? We like we did in the real case, I multiply this mess by, let's see, in the past I would multiply by the same function, but now I'm thinking of complex inner product. So I'm going to multiply this by e to the minus I mx. I'll multiply this one here. And then I'll integrate from minus pi to pi. Do it here also. And then I'll put the sum on, I'll interchange the sum with the integral and get a sum. Let's see, that's going to be a sum from minus infinity to infinity of Cn. And now I'm going to get an integral from minus pi to pi of e to the I nx times e to the minus I mx dx. And of course, those are all 0, except for the n equal m case. And so this is mostly 0. And it's equal to 2 pi when n equals m. And so that big ugly sum spits out something simple, namely just Cm times 2 pi. And that gives us the famous formula. I guess I skipped a dx here. So that makes it a whole lot easier from the point of view of complex notation to get the formula. Okay, well, I wanted to introduce you to the complex notation because we're going to get more and more comfortable with it as the course goes on. And we'll use the power of this approach and the simplicity to make major progress in understanding Fourier series. But that's enough work for today. Now I'm just going to mention some fun things. So some fun facts. Let's go back. I'm going to go back to the real version. real version of the Fourier series. So in the real version, I write f of x equals a naught plus a sum as n goes from 1 to infinity, a n cosine nx plus b n sine nx. And let's see, the cosine nx functions are all even. And the sine nx functions are all odd. And a constant function is even. If it was 0, it would also be odd, but of course, the only time it would be both even and odd is if a naught were identically 0. So I'll consider a naught to be even, since it doesn't have to be 0. And here's the fun fact number 1, is any function can be expanded as a sum of even and odd function. So here's a fact. Any function equals an even function plus an odd function. And the decomposition is unique. I'll ask you in a second how you would show that it's unique. Okay, so let me show you how you do that. F of x is equal to f of x over 2 plus f of x over 2. Everybody believes that. And now I'm going to write here plus f of minus x. That makes that thing in the first spot an even function. Because if I put in minus x there, it doesn't change. And then I put here minus f of minus x. And now you realize, I didn't change the function because I have plus and minus the same thing. And so it doesn't change it. And this one is even, and this one is odd. Why would the decomposition be unique? Yeah.
So you can assume another decomposition and then subtract the two sides and then find each representation of 0.
Yes. Then you would have, if you had two of those things, you could subtract them, and when you look at it, you'd see that, I can combine the even functions on one side and pull the odd functions to the other. And I would have an even function is equal to an odd function. And when you put in an f of x there, you'd see that, f of x has to equal f of minus x. What do I have to see? You'd see that f of x has to be equal to minus f of x. And that only happens if it's the 0 function. If you think too hard about this thing, you realize, what about 0? And in turn, if the f is discontinuous at 0, then I could make f be 1,000 at 0 and screw that up. So I guess if you want, you would have to add that if it's continuous at 0, then it would also have to be 0 at 0. And there'd be only one way to do this. But of course, we're going to be dealing with continuous functions. So it's unique decomposition if the thing is continuous at 0. Maybe I should make a little remark there. When continuous, well, let's see, it could be 0 at 0. That'd be fine. When f is continuous at 0. Okay, it's a nice, when you're dealing with Fourier series, especially in the real case, some useful facts to know. if f is odd, then let's see, we got cosine terms which are even and sine terms which are odd. So if f is odd, all the cosine terms are 0. All the an terms, including a naught, are 0. These are all the cosine terms and the constant terms. If f is even, then it's the other ones that'll be 0. If f is even, all the bn terms have to be 0. And those are the odd ones, so that makes easy to remember. These are the sine terms. And the y is easy. Let's see. Let's take a case here. I won't do all the cases. Integral from minus pi to pi of f of x times cosine n of x dx. Let's see. If f of x is odd, for example, cosine nx is even, and I'd have an odd function times an even function. And an odd function times an even function is odd. And when you integrate an odd function over a symmetric interval, you get a big fat 0. Because minus pi pi is a symmetric interval about the origin. So I can do this without doing any calculations. Okay. So I guess rather than get carried away with this, let me do it by pictures. Let me think of an even function. Let's see. An even function might look like this. It's got to be the same on both sides, so kind of like that. Okay, and when x is here, then you look over here at minus x, you've got to get the same value. So here's a fact when f is even. F of x even, and that simple fact is that the integral from minus a to a, the symmetric interval of f of x dx, if I think of little delta x's there on both sides, I realize, oh, those little rectangles have the same area. Or I could do a change of variables in these integrals and see that that's 2 times the integral from 0 to a. That's a nice thing to know. Simplifies some formulas. And when it's odd, I would get 0 there because they'd cancel. I guess I have to draw the odd case. In the odd case, I'd have this here and then this over here. And they would cancel because then I would have over here x and minus x. That's supposed to look like it matches. Minus x. And those would be negative each other. And I would get, when f of x is odd, the integral from minus a to a is 0. Like that. That's an important thing to do. And the simple facts that I mentioned, I just did one of them, but I should write them all out. Let's see. Even times even function is even. And an odd times an odd is also even when you write out the definitions. And an even times an odd is odd. So that's what you'd use when you see that the certain coefficients are 0 in the even and the odd cases. So because of these facts, what we can see today at the end of the lecture is that both we understand the Fourier sine series, the Fourier sine and cosine series, which are valid on 0 to pi, when I did the vibrating string problem, pop out from the full Fourier series. Okay, I'm going to show you why. Let me do the sine series case. So an example here, just to show you. Remember when I did the harpsichord problem, I could take my f of x from 0 to pi. There's 0, here's pi. And then if I extend it as an odd function, then I get, so this will be the f star here. I extend as an odd function. And then I write out the full Fourier series. F of x equals, I won't write it out, but you get the full Fourier series. And because it's an odd function, all the sine terms are gone. I'll write this out more carefully when I post the notes. All the sine terms are gone. No, all the cosine terms are gone, including the constant one. It's an odd function. Okay, and you get a summation of n equal 1 to infinity of bn sine nx. But the bn's in the formula here would be 1 over 2 pi, integral from minus pi to pi of the star function. But that's f of x sine nx dx. Okay, this one's odd. This one's odd. And so their product is even. And therefore this is 2 times the integral from 0 to pi. So 1 over 2 pi times 2 times the integral from 0 to pi